Hello there. Today we'll be doing making change SQL. We'll be given denominations of 1, 5, 10, and 25, and we're trying to find how many coins it takes to get to 60, and I'll put it here as 3. It takes 2 quarters and 1 dime to do it. You might be thinking, oh, this is a simple problem that we can start by just taking the 25 coins and then take the next coin, but we can't do that. Of course, if you look at this particular example here, 3, 4, and 5, you can see that we can make, if we start with 5, we'll get to 7 in 3 ways. But if we start at 4, we can get there in 2. So that's not how we can do it. We have to try every different way, starting at every different position. That means backtracking. But we don't need to do exactly backtracking. We could do some memorization when we're doing that, and because we're repeating problems. Why are we repeating problems? Well, the repeating of problems is that, let's say we're trying to get to 7 coins. We try to throw in 7 in the algorithm. What happens is that when we take 1 less coin, that's 6. We need to try to get 6. Or we try to get 3, and we put 3 in. We're trying to get 4 now. We're trying to get 3 now. We're trying to get 2 now. And after that, from 6, oh, look, we can add 1 coin again. And then we can add 3 coins again. And we can add 4 coins again, or a 5 coin, right? And that means that we subtract that, and we get 5, and then we get 3, and then we get 2, and then we get 1, so on and so forth. Of course, you can see here, the 4, it will take us to 0, which is 3. It takes if we get to 0, that means we've found our answer, and we can roll back up. That's our base case. Roll back up to our 7 and tell them, oh, look, we found the coin, the number of coins needed. Every time we add a coin, we add 1, and then we add another 1. And when we're going to get to 0, add 0. And that's how we get to our answer of 7. Of course, you see a lot of repeat problems here. You see the 3 here and the 3 here. Of course, this 3 gets to 0 too. What this means is that we can build up our answer using memorization and storing that information so that we don't have to repeat the process, which brings us to O of n. Of course, there's the bottom-up approach, which starts at 0 instead and starts building up from that particular point. How many ways is there to get to 0 from 1? If we had 1 denominations, we can't get there sometimes. We can here, and it takes 1 coin. And then for 2, it takes 2 coins. And then for 3, it takes 1 coin. And then 4, 1 coin. And then 5, 1 coin. And then 6, well, 2 coins. And then for 7, well, we look back for 3 coins ago, and oh, look, 3 coins. So this is a dynamic programming question, which basically means we store information. We can go top down. We can go bottom up. Well, we can go through recursion. And I'm going to show you 3 ways to do this. I'm going to show you the recursion. I'm going to show you the top down. And then I'm going to show you the bottom up. So I'm going to present 3 solutions today. And so stick around. Here we go. So to do the recursive solution, I'm going to create a recursive function called makeChange of the change of C. And as our base case, if C equals 0, we're going to return 0. Otherwise, let's set the current min coins, and the min coin is equal to math.inf. Because we're going to have spread out 4 different ways, or the number of denominations, and we have to check each way. So if C, so 4 denominations, and if our current change minus the denomination, the coin, is greater than or equal to 0, that means we can make the change. It's possible for us. We can set current min coins equals make change. That means we're looking at like a smaller amount. What happens at a smaller amount? Can we make change? And how much that change? How many coins do we need from that? And then we set the min coins equals the min of current min coins and min coins. One question you might ask: why do we do this here? Why don't we just do it here? And you're right, we should just do it there. And so let's just finish that. Return the min coins. This is every time we get an answer, so let's add 1 to it. If min coins at the end of the day is equal to math.inf, else we're gonna return -1, which is what we need to do. So very simple. We're just gonna return make change and our amount, and it will use the denominations in our solve problem. So let's run. Okay, denominations is spelled incorrectly. Let's copy and paste. Let's run. All right, so we can get to 12 easily, but the problem is when we try to get to like 60, and we're gonna get a time limit restriction because it takes way too much time for us to get to that particular denomination of 25 and 25, and then and get to our answer. And so we need to do better, which means we're gonna do memorization. So what that means is pretty simple. We're gonna create a cache, and we're gonna store that information. Remember, default dict, we can set it to -1 automatically, and we can set the 0th item to 0 because we know it takes 0 things to move to 0. So with that, we can do we need to do a non-local cache? I'm not sure, but if we do, we will see that soon. So we're gonna create a cache for our item. If it's less than or equal to 0, we can just return the cache. That means we don't need to look further anymore. We have found our answer. Otherwise, same thing as before. Set the current coin, min coin, math infinite, cd. Do the same thing again, but this time, what we're gonna do is that we're gonna store the answers. So basically, that means instead of returning immediately, we're going to say a cache of C is equal to the min coins plus 1. And we're going to return the cache of C. And we're going to make change with the amount, right? So one thing is, if the cache, we're not going to return make change anymore. We're going to run make change, and then we're going to return the cache at our particular location. So return cache at our amount if cache amount, and it should be -1 if it never gets there. So it should be fine. So let's run. So 3, very good. So we can do that now. We can get to 60. But the problem is, let's say try something super small and something super big. Like we'll never get there. Let's run that, and I think we have some sort of issue where we have a dump of some sort, and that's the problem with this particular case. We just can't. We go through. We're storing too much information or something. I'm not exactly sure what it is. I looked it up, but couldn't find the answer about that one. I was not too interested in the field, this particular field, because this problem doesn't come up too often for me. So with that, I think it's time for us to go through what exactly happened here in this particular question, and then move on to the bottom up. I was going to just move on to the bottom up, but we can go through the question. So we created a cache with all -1s. And what we're going to do is that we put in the 7 again into make change. And the 7's not in there. So we try to look for the denominations. We try to look for 6. The 6 is not in there. We go for the 6 and we try a 5, and the 5 is not in there. And then we try a 4, and then 3, and then 2, and then 1. And then get to 0, right? So it takes 7 coins to get to 0 at this point. And of course, once we've done that, what we do is that we go like, well, let's try something else. How many coins does it get to? Let's say 6, and then we try a 6 coin, and and so on and so forth. Let me just print it out. It makes it a lot easier. Let's just print it. And let's go back to our original test case. Oh, shoot. Okay, original test case, 1, 5, 10, 25, and we're doing 60, I remember. Run. So we start at 0, looks like we go up all the way to 4 coins to get to, we did a 1, 1, 1, 1, and then we did a probably like a, no, actually, I think we did, I don't know exactly what we did here, I'm not sure, but we ended up with 4 coins. And then we start at 0 coins again, 5, and then, weird. 7 coins, the maximum that we have ever seen. So yeah, I don't know exactly which branch that particular item went down. Yeah, I'm sure we save some information somewhere and we pass it back out. Okay, so that's very, I mean, if you're interested, we can discuss this in the comment section later. Let's get to the final path, the solution to this problem, which is a bottom up. We're going to start at 0, and from 0, we're going to go to the top and find out how many coins does it take to get to 1, how many coins does it take to get to 2, and how many coins to get to 3. So this means we're going to set dp equals the amount plus 1 times the amount plus 1, so that we get the proper amount of items in our dynamic programming. And we set the 0 to the 0. So like, oh, look, we're going to get to there in 0 time. So A in range for amount, in range, amount plus 1. And for D in denominations, we're going to do if amount minus denomination is greater than or equal to 0, that means we're not hitting some negative spot. dp of the amount is equal to the minimum of the dp of the current minimum, or, which is amount plus 1 at this point, which is basically means that it's a single coin every single time. Wait. Well, it's still more than the amount, so it's more than 1. So, okay, we're good. Okay, so that means that we will not have a issue where we have one single coin adding up to the dynamic programming amount, and we'll have a issue with computing wrong one. I mean, if it just works and then we say it doesn't work, which is really weird. We don't want that. So A minus D, which is the amount minus denominations, we're checking, okay, let's say we're at currently 7. Let's go back to 4 and see, oh, look, how many coins does it take there? It takes 1 coin. And that means that it takes a total of 2 coins to get to 7. So let's return dp of amount, if amount of dp amount it more than or equal to does not equal to amount plus 1, else minus return -1. Run and submit. And that's it. That's how we solve making change SQL. Again, let's see what we learned today. What we learned today to do a dynamic programming question or figure out that this is a dynamic programming question is that what we did is that we looked at how we could solve this problem and looked at a naive solution. We did a top-down solution to show that, oh, look, we could store these answers. And then we did a bottom-up approach where we built up to the answers. And that's how you would approach this problem in an interview, I would say. Unless oh, I've seen this problem, let me just do a dynamic programming and whatnot. You can do that too, maybe. I don't know. But I think it's best to show that you can think through these topics and understand what is going on. And I think that's what we're trying to learn here, how to see things that we can store and reuse them. And that's the dynamic programming for this particular problem. Well, if you have any questions, please comment below. If you enjoyed the video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and I'll see you in the next one.